Good morning. Welcome to our presentation on scaling data management for machine learning. Essentially, the purpose of today's talk is going to be talking about the importance of and need for a research data infrastructure, we would refer to here as research data as a service, for supporting clinical research and AI activities, at scale in a clinical environment. So if we start at the beginning, why do we even care? Under normal circumstances, we have lots of change going on in the clinical environment, move to outcomes-based compensation, the drive towards precision and personalized medicine, desire to improve quality of care at the same time while reducing costs. And there are many, many opportunities for innovation, as we'll talk about in a few minutes with all the advancements in technologies. But there's also a huge risk of inaction. If you don't keep up, it could put your organization at risk. And then obviously in today's world, everything is complicated and by the COVID-19 scenario, and there's many research projects and development opportunities to address the challenges associated with COVID. And all of these are huge opportunities for leveraging data and machine learning going forward. So rather than talk in the abstract, I thought I'd start with a very pragmatic real world use case. Our colleagues at the University of Wisconsin have recently completed a project to develop a machine learning ensemble model for identifying COVID-19 in chest x-rays. So it ended up being a fairly sophisticated project in the sense that it generated an ensemble model of many different AI models that kind of work together, and you kind of pick the best score. And at the end of the day, it's a very high performing result. The way they got there, though, it was fairly complicated. Ultimately they included, nearly, kind of in the neighborhood of 50,000 data sets. There were multiple sources of data, including, by the way, chest x-rays, as well as PCR test results from the EMR. They wanted more data, so they partnered with another health system to get data from 5 additional hospitals and to get a large enough sample set. And then, of course, they ingested additional control data from NIH. So, pulling in a large variety of data, then the challenges become, sort of organizing, searching, implementing a labeling workflow to accurately label the samples for the training process, which involved image annotation and custom metadata. And then, of course, setting about to train the model, of course, various iterations and the different models, just that whole workflow and organizational process. And then, of course, you have to test everything and evaluate it. And to make everything more challenging, the team was all working at home due to the COVID distancing requirements. And so, how to, the basics of just even how do you access clinical data securely in that context were some of the key challenges. So this is kind of the backdrop, this and similar scenarios is what we're here to talk about today. And then I'll come back to more specifically some of the ways we help in some of this specifically. So stepping back a notch, you have, huge potential value in your clinical data. You've got, huge volumes of data with untapped potential that involves your imaging data, but it could also involve EMR, genomics, digital pathology, many other types of data that are maybe not classically imaging. And you've got all this technology innovation, machine learning, big data analytics techniques that can scale beyond anything previously possible. Cloud scalability, GPUs, TPUs, all these technologies that allow you to get, glean more value from that data. And at the same time, huge opportunities for collaboration. Multi-center studies, gather, as the previous example, gathering data from across multiple, institutions, and collaborating to solve the problem. The problem is most organizations are really not very well prepared to deal with these kinds of things. So you have, the data is really just not even fundamentally ready. It's not labeled or annotated consistently. Just simple example would be, radiology reports being unstructured largely. How do you put structure behind those? Labeling things consistently from multiple sources that may use different techniques for the data, image annotation, all sorts of things, quality control. We'll talk a little bit more about all these. You have all this compute power, but the scale and complexity of accessing that, many hospital systems are not really prepared to deal with the, kind of the IT challenges associated with that. And, so how can we make that simpler? And then at the same time, while there's all these opportunities for collaboration, the data privacy and compliance risks are really critical. Security, data privacy, and so on. So those absolutely must be addressed. So kind of stepping back with a little higher level, a lot of what we see is, maybe a main driver for machine learning is, personalized medicine, getting more specific about how we can deal with an individual patient. That often involves the idea of getting a more, complete view of subjects. I kind of here we kind of refer to it as a 360-degree view of the patient. We've heard Siemens and others refer to it as a digital twin, where you're modeling as much as you can in the digital domain about the patient and trying to understand all the interdependencies. So the challenge, of course, is you might have multi-modality imaging, but even non-imaging data, again, EMR, genomics, pathology, that type of stuff. And, you got to get that in one place and be able to work with it in a consistent way. And then the challenge is how to sift through all of that, sort through it, prioritize it, to improve screening, diagnosis, and treatments, and ultimately improve quality of care. So this is sort of the big opportunity to leverage data science and machine learning on top of all this wide variety of data types. And then the one thing that many organizations underestimate is that this isn't a one-time thing. It's an ongoing process. You don't train a model and you're done typically. You train it, retrain it, improve it, refine it to make them better. And it's a system, it's a process to improve those algorithms. And so an infrastructure to make that happen, and make that manageable and scalable is really the key. And if you just look at it from a pure machine learning point of view, there are many studies that say, broadly, 80% of machine learning is the data management challenge. And I won't go into all of these here, but they should be familiar. There's a lot of work that goes into preparing data and getting it organized and labeled and curated to be ready to support the machine learning process itself. And so you need an infrastructure that's going to scale there. Now, what we see is many organizations are sort of saying, well, this kind of feels like my PACS and VNA, maybe I can just extend that and create an infrastructure to support my research activities. Well, the problem is their clinical systems are pretty different than what a researcher needs, just in the normal context of research, but also in the context of machine learning specifically. So, clinical systems, you're going to deal with individual patients, generally, security is set up to, enable anybody who's providing care to be able to quickly access, patient records with PHI, that kind of thing. And, it's about running, specific transactional sort of FDA approved tasks against the data to deliver care. Search is typically limited, metadata is kind of typically limited to, broadly accepted, but, kind of shallow standards. Whereas on the research side, it's quite different. You're typically trying to organize data into cohorts. You may involve imaging and non-imaging data in the same project. You may have a number of collaborators who really don't need to see PHI. They're technical people, engineering people. So you want to minimize risk there. IRB compliance, just keeping the scope of work and the scope of participants and the scope of data, constrained to what the IRB requires. De-identification, different types of workloads, big, large experimental pipelines, batching, reprocessing, all of that kind of thing, not to mention handling non-standard data along with your standard data and custom metadata. And then ultimately, the ability to really understand all of the data that you have in one place, kind of searching across the entire system. So your teams can be more effective at finding the data they need, curating it to the standard they need for the machine learning or other purposes. And so these systems are really different, I think, is the main point here. And the way we would think of this is as what you need is a platform that delivers research data as a service. So this is, essentially an infrastructure that's kind of parallel to your clinical infrastructures that enable you to manage research data at scale, and more rapidly deliver clinical information, clinical data, imaging, non-imaging data to your research community, while dealing with proper governance, privacy, security, compliance kinds of activities. So at the high level, what we're talking about here is being able to create a research repository that can deal with imaging and non-imaging data, deals with de-identification in a systematic way, supports the curation and quality, labeling, annotation kinds of processes, can handle image processing, really complex object processing, can handle and support machine learning workflows, can support analytics, and do all of that in a secure collaborative framework, that's again designed around a research workflow. And then, what that does is empower then your research community to be more productive, whether that's involving, MDs or, data scientists and, engineers and other things. And again, the purpose here is to, systematically make data available for machine learning, imaging research, development of new personalized care apps and so on, while protecting that data and, and dealing with the appropriate governance. And so this is where, our company, Flywheel, comes in. We've developed such a system. We focus really on research and related non-clinical care delivery kinds of applications in a way that goes well beyond what a clinical system would typically do. So at a super high level, it's a software system, can scale from, a departmental level, a lab, but it can go all the way up to very large enterprise deployments, let's say, institution-wide deployments. There's technical reasons for all that with the scaling. But broadly, what it does is enable you to capture your data, whether that's imaging or non-imaging data, de-identify it on the way in. It's, essentially it's creating a repository, a database that, can allow you to organize and structure and label this data in ways that go beyond maybe the limitations of your current clinical systems, can meet the needs of individual projects, or can also meet the needs of kind of broad ontologies and so on across all the data. It provides a computational framework for automating image processing, machine learning workflows, that kind of thing. APIs for integrating with your existing systems and so on, so you can, it's very researcher friendly in the sense that it's not designed to get in your way. It's designed to help you design your projects and studies and work effectively. So very open science-based approach around computing. And then a big difference here is that everything is organized around projects with secure collaboration in mind. So you have security, role-based access controls. You can define roles to meet the needs of your protocol and workflow. But broadly, it's enforcing your IRB compliance and essentially improving your risk profile as you're making data available to the researchers. You're also sort of minimizing the need to copy data as much, and with compute in place, you kind of again reduce the need for additional copies, and you've got another level of access controls and logging and all the things that you would expect. So it's a data research data as a service platform. We started in academia, but we've expanded broadly into clinical research at research hospitals and hospitals. Our largest customer is very large life sciences customer. I'll show an example of this in a minute. AI developers who are licensing healthcare data need to do the same types of curation, broadly to support their machine learning or again, imaging research, and also because it's web-based and very secure, we're very well suited for multi-center studies. So that's a little high-level background on what we do and sort of how we go about it. But broadly, as I outlined, the need for a research-first sort of approach and a research infrastructure, that's what the system is. And I won't go through every detail here, but it's a comprehensive research workflow that addresses everything from capturing the data, organizing the data, processing and analyzing the data, and doing it all in a secure and scalable framework. Just quickly, I'll run through a few examples of how this type of solution can be defined, and then I'll come back to some specifics on the machine learning and the example we talked about earlier. But just to give you a feel for how this, this kind of research data as a service infrastructure can be deployed. One very common use case for us is core facilities, dedicated research, imaging research centers, in a solution that automates everything from data capture to secure collaboration. So in a scenario like this, we're typically connecting directly to the dedicated research magnets, automatically capturing all of the data, de-identifying it on the way in as needed, and then ultimately delivering that data into a comprehensive repository that supports the research workflow. And then users, kind of collect their data there or work on the data there, as teams in the context of projects. And so we can collect the data from the dedicated research magnets, but you can also opt in to send clinical data into the same system. And in fact, it's not limited to, maybe the case I'm talking about here is mainly MR facilities, but other modalities can be introduced, whether that's EEG or digital pathology and other types of things. So we have many examples of this, but it's a way to deliver better service to the labs and while improving productivity and reducing costs. And so it's just a comprehensive way to share data and enable people to collaborate more effectively while conducting their research and improving reuse and reproducibility and so on. A very similar situation is doing the same type of thing, but doing it with clinical data as the centerpiece. So multi-modality clinical research. So, in the context of med schools or hospital systems where we want to share, imaging data, EMR data, that type of information, maybe some EDC data from a system like REDCap, get that data into the hands of the users while dealing with the same types of issues, organizing, labeling, positioning to share and reuse that data more effectively, while supporting a productive workflow around tasks like machine learning and precision care. So essentially it becomes sort of a governance system on one side, but also a productivity tool that the labs and the researchers in those labs will find very useful in terms of supporting their work. So it's not just governance imposed on people. It's kind of a productivity tool at the same time. So again, clinical research deployments, and this is really consistent with the use case I showed earlier with the COVID ML application at Wisconsin. Another scenario, which is clinical research related, but it's in the context of large pharma. Our largest customer is actually one of the largest pharmas in the world, who are going back and pulling in retrospective clinical trials data and curating that to a common standard and making a research repository that they can then build new analytic processes and machine learning applications against to, deliver personalized care and AI solutions to the market. So they've long recognized the value of their data, but now there's infrastructure and tooling in place that makes this the process of ingesting all of that data and organizing it feasible. And we're doing that in this context. And maybe in the context of, many of you being in the world of working in hospitals and research hospitals and so on, maybe the main point here is you can do the same type of thing. They're pulling in retrospective data, and you can do it at scale. This particular system has millions of data sets and millions of jobs run against that data, and scales very well. So as I was saying, those examples here are useful just to maybe set the context, but broadly speaking, in terms of scaling for machine learning, there's kind of a balancing act here, which is really important. To make a system like this useful, you really need to kind of balance the needs of the project teams trying to get the work done. Historically, I think if you talk to your researchers, they're going to say that they feel underserved in terms of the ability to get access to the data and tools that they need to be productive, and so on. And so we feel really strongly that any solution that you provide has to be oriented towards the productivity of those teams, making their lives better, making it easier to work faster, make it easier to collaborate, be open, flexible, so that you're not imposing unnecessary constraints on them. Scientific reproducibility is critical. The provenance, the ability to systematically reproduce a study, for scientific integrity is critical. So helping them do that work is a key part of the equation, and that's where having a research-centric solution makes a big difference for them. But at the same time, you have to be aware of your governance responsibility. On one side, you want to promote the positive aspects of reusing data, gaining insight, across the organization and so on. But that the institution also has to scale that while dealing with security, which is critical, of course, and dealing with data privacy and other compliance challenges. For example, FDA 21 Part 11, that kind of thing. So this is very much how we view the world: is providing a sustainable, scalable infrastructure that meets the needs of the institution, but at the same time, really a strong focus on the productivity in the labs, and helping them develop AI algorithms and machine learning, image processing algorithms faster. They make a difference. A big part of this is data management and sharing, and in NIH terms, they've framed the FAIR principles, and our approach to this is very much in line with that. So you want to make your data findable, accessible, interoperable, and reusable. And we address that, through metadata and search being a strong centerpiece of the Flywheel system. Accessibility is, web-based, open APIs and tools for programmatic access to everything. Interoperability is critical, and there it's comes through standards wherever possible. And then in our context, reuse is not only data reuse, but a strong focus on reusing and sharing algorithms, so that people can build on each other's work in a very reproducible and scalable way. So I won't go into all the ways we do that specifically, but this notion of essentially creating a data repository that's designed to enable you to find the data you need for your purpose, reuse it where appropriate, and be productive in that context. Work faster, work more effectively together. It's a big part of our approach to this research data as a service model. Not surprisingly, by the way, the cloud is a very important way to scale this work. In the long run, we think everybody will ultimately be in the cloud. Not everybody's ready to do that today, so of course we can deploy in on-prem infrastructures, and we're working with all the major cloud vendors around their cloud-in-a-box solutions, hybrid infrastructures and so on. But in the long run, the ability to access large amounts of compute and storage on demand is really important. So the data management works really well. The computation in particular, with elastic scaling in the cloud for running large AI training jobs or large data analytics, and the idea that you can kind of pay for what you use as you go is really important. And then collaboration is also enhanced by kind of working in that environment. So anyway, one way we address this from a scalability point of view, and also a manageability point of view, is to offer this in a way that you can take advantage of the cloud, but in fact multiple clouds as appropriate, and take advantage of your own local infrastructure. So you're in kind of a hybrid environment. So Essentially what we're showing here is the idea that you could, deploy on-prem or in the cloud and pick your primary cloud vendor, for example. But, individual labs could also choose to, excuse me, to run their applications in a specific environment of their choice. So for example, let's say you deployed on Google as your primary cloud storage provider, but somebody got some machine learning credits from Amazon, they would be able to set their specific projects up to run in the Amazon environment, but still take advantage of the security framework and the database and search and so on. And likewise, we can also allocate work to your high performance computing cluster that the university might have, or even dedicated GPU nodes and so on in the network. So technically, it's very powerful in the sense that you can kind of work where you want to work while still kind of providing a governance framework and a reuse framework. The other big benefit is, from a practicality point of view, when you do this, you can also manage and allocate costs to various cost centers. So the work's being done in a lab's given account. Their charges are going directly into their account. So you're not in the internal billing and allocation business. You're essentially just directing the work into the appropriate account, and the bill shows up at the right place. So it's an important way to scale. It kind of sounds mundane if you're mostly here to talk about machine learning, but it's a very important aspect of being able to scale data management to support machine learning. So let's talk a little bit more about machine learning. At a high level, we approach the problem in the following way. One is being able to ingest clinical data, imaging, non-imaging data, help you prepare that data for training. So that's the curation process, image annotation, those types of activities. And then we also have this computation framework that can be used to automate the training and retraining processes, so that you can build models, score them, that type of thing, track all the metadata, versioning, all those sorts of things. And then provide a framework that you can use to test those algorithms in context even. Maybe deploy those against new clinical cases as they come in, and evaluate their efficacy and so on. And we don't really get into which tools you use. It's your business to decide whether you want to use PyTorch or TensorFlow or some of Google's cloud technologies or others. We provide a framework for managing this, but it's totally up to you to select the particular tools of choice in that context. But one very important part of this is, by working in this kind of a framework, we're tracking everything. So you're getting, detailed provenance on who's doing what versions were trained on what. So if you're ultimately going for FDA approval, that type of thing, you'll have all the detail that you need to support those kinds of activities. So this is at a super high level how we fit. If we look at it from sort of a different point of view, what a research data as a service platform will let you do is sort of create an environment where you can find the data that you need. We do this by getting the data into the system, of course, de-identifying it to deal with the privacy issues and so on. But there are systems inside our tool that help with labeling and classification, and everything in Flywheel is searchable. So in the little example on the lower left here, we're showing, MR data that might come in labeled in a wide variety of ways, but the classifier internally is, recognizing generally, this data on the top here is, it's a structural T1, and this, next data set is, T2 weighted structural data, and so on. So when you want to go back later and find similar images, just as one trivial example, you can find those. We could also pull in some of our team members, for example, recently worked on a project that extracts 27 different TBI factors from pathologies from radiology reports. So it parses the text, puts the structure into the Flywheel system, and then you can search for anybody who had a cerebral hemorrhage or some other specific pathology that you're searching for, as an example. So finding the data, finding the cases, and then maybe going back and getting the details, based on those relevant cases. That kind of thing can be set up using a system like this. Quality, really important to understand what you have and what you're working with before you go into your training process. So we can automate routine quality processing using our compute framework. So new data lands, we say, oh, that's let's say, it's functional MR data or structural MR data. We could apply, the appropriate quality control algorithm for that type of data. Score it, add the metadata, metrics, quality metrics to the database, and then you could, search and say, oh, these are intolerance, or within tolerances, or with, outside of tolerances. Even doing basic phantoms and comparing the quality of your scanner over time, that kind of thing can be done. Then, of course, we have a whole complete framework for labeling and annotation of data. So if you're adding custom application-specific annotations, in the case of the COVID project I mentioned, they created some custom metadata to identify, whether the COVID existed or whether it was, the image was related to previous, pneumonias or other types of factors. So they were able to set up an application-specific metadata scheme for labeling. But we also have tools for going in and drawing specific ROIs and setting unique labeling, building qualitative summaries, the kind of thing you might do in a spreadsheet otherwise, and keep that all in metadata, all searchable, and make that easy for you to find the data that you need to work with to create your training sets, your test sets, and so on and so forth. And then, of course, we can help you automate the actual training and testing processes. So broadly, selecting the data, running a training process, keeping track of the relative scores of those various iterations, and then tracking all the provenance necessary to understand which ones are working and which ones are not, and the details behind them, how it was trained, who trained it, what were the options used, all that kind of detail that somebody's got to put together. We largely help you automate that with little effort. So again, find the data, improve the quality, annotate, and then you can kind of focus more effectively on your machine learning. And again, all of this is in the context of IRB compliant, secure projects with the appropriate levels of de-identification enforced. So kind of back to the COVID example. This is sort of been implemented on the system I described, and the team there has told us that they really couldn't have done it without us. Just with the basics here, they everybody was working from home, and they just didn't have access to the underlying clinical data. So they one of the team members was able to get it ingested into the Flywheel system and create the appropriate projects around that. And so then they were able to have a secure access point for that data. They, as I mentioned earlier, they did all their labeling workflow, customized the metadata so then they could search for COVID cases versus various control scenarios, all that kind of thing. Very easily create various cohorts and organize that data, ingest their blind reader study information from the human reads, and be able to set up the processes to report and compare that type of data. But it was all because they had a system they could do it. So everything was data-based in a secure project, enabled these people to work from home. And honestly, I don't know all the details of how they actually implemented the various models, but the teams, then had access to the data and were able to, kind of work effectively to build and score the various models and ultimately generate a very high performing system. So I understand there's some paper coming out soon on this, so I'm not going into a lot of detail here, but at a high level, this shows the power of having a research data as a service kind of infrastructure, to enable productivity on, just one example that's relevant in today's context. But this could be, a similar scenario for a broad range of applications. So I think we'll wrap it up here. Hopefully we've made the case for why a research data as a service model in your research environment is useful and important. You've got many demands for data, you know, many driven by machine learning. You know, how do you maximize the value of your clinical data to support your research community? You know, how do you fuel collaboration and innovation, you know, and do all of this while, you know, scaling and at a cost, you know, at a cost-effective level, while continuing to ensure and improving your privacy and compliance. And we think this research data as a service model is a very effective way to go. Hopefully you found that useful. If we can help you with any additional information on, you know, how we address it specifically, you know, feel free to reach out. So I think we'll wrap it up here. And I think the next step is to open things up for Q&A. Thank you again for attending.